now that we already understand the pattern that can be observed on the screen, if we have a double slit experiment, let's try to relate between the various variables for this Young's double slit experiment. So I'm going to clean up the diagram a little bit, make it neater to be seen, and we are going to draw various lines on this diagram over here to illustrate the relationship between various variables. Okay, for now I'm going to focus on constructive interference, and I'm going to derive an equation that relates between various variables for constructive interference. The first variable that we're going to relate is the distance between the two slits, which is represented by this small d over here. We also have this big D over here, which represents the distance between the slits and also the screen on the right. This distance here is represented by big D. Okay, so they are the same D, which represent distance, but small d is the distance between the two slits, big D is the distance between the slits and the screen. Okay, you also have this distance Y over here. This distance Y here represents the distance of a particular fringe, any fringe that you are interested in, from the central bright fringe. Okay, the measurement is done from the central bright fringe to the fringe that you are interested to study. Let's say for this situation here, I'm interested with the first bright fringe after the central bright. The first bright fringe after the central bright. So if I'm interested with this particular fringe, I can find the distance of it from the central bright fringe, and it is represented by this symbol Y over here. Okay, now our objective is to create an equation that has Y, that has D and big D in it, and we are going to see how they relate to each other. Okay, so we are going to use a bit of geometry to understand the whole situation here, so it's good to draw along maybe. Okay, so for constructive interference, we know that R2 minus R1 is equals to M lambda, or in other words, the path difference between source 1 to the point of interest and source 2 to the point of interest. The path difference here is an integer multiple of the wavelength. Okay, it can be 1 lambda, 2 lambda, 3 lambda, any kind of integer multiple without decimal place. Okay, so R2 and R1 over R2 minus R1 over here means by the difference in the two paths that we have over here. Technically, you can see for this particular bright fringe over here, we can see that R1 will be a longer path, whereas R2 will be a shorter path. But where exactly in the diagram can we represent R2 minus R1? Or what we want to try to say is R1 and R2, the difference is in which exact part of the diagram. Where can we label the R2 minus R1 in this particular diagram? Okay, so to understand that, we will first start by drawing a perpendicular line perpendicular to this first path over here, perpendicularly coming out from this first path, and connect to the source 2, the point, the slit 2 over here. So first start by drawing a dotted line over here to perpendicular out from the first path to slit 2 over here. It's just for geometrical purposes, later you will see why. Okay, so once you have drawn this line already, we can now label where is our R2 minus R1. Okay, so basically based on what I label over here, I can say that the difference between the first path and the second path is represented by this part only. Just now I say that R1 is longer, R2 is shorter, right? But R1 is short. R1 is longer by how much? It is only longer by this tiny amount only. Okay, this tiny amount makes the difference between R1 and R2. But if you just by looking at this diagram here, you might find my words a bit not convincing. Okay, because if it's a triangle over here and I say that the difference is only in this part only, what I will be saying is that the distance from here, this particular point of intersection, from here to this first bright fringe, and the distance from here, source 2, to this first bright fringe will be equal distance, because you are saying that these two are the same length, just that R1 has an extra which is over here. Okay, this is what I'm trying, or this is a statement that I'm making right now. Okay, you might find it not convincing, and the answer is yes. Actually, the answer is not exactly true, but it is still a good approximation to be made. Why is it a good approximation to be made? Because in an actual Young's double slit experiment, this small d here will be on the orders of millimeters or even micrometers. The distance between the two slits are very near to each other on the millimeter or micrometer scale. Okay, but this big D here, the distance between the slits and the screen, is on the orders of meters usually. Okay, so if you compare millimeters or micrometers to meters, there's a difference in 3 to 6 order of magnitude. It differs by around 1,000 times or to 1,000,000 times. Okay, so the difference is so big that you can think of this screen, if you want to draw it according to scale, this screen should be out from your phone like very far away. Okay, you should probably be putting this screen like 5 or 6 A4 paper outside of this screen, then only you put your screen over there. Okay, the point I'm trying to say is this whole diagram here is not drawn according to scale. If you really want to draw it according to scale, this big D here will have to be at least 1,000 times to 1,000,000 times larger than this small d over here, which is somewhere very far away. Okay, so I can try to approximate how does very far away looks like. It will sort of look something like this. Okay, so technically what I'm trying to say is you are not able to see where is the screen. Okay, if you place the screen somewhere very far away and you're only focusing on the early part of this diagram over here, technically if the screen is super far away, which might be a bit difficult for you to imagine, this line over here, this line representing R1 and this line representing R2, the first path and the second path, will be nearly parallel to each other. Right now, if you look at it like this, you can see that there's a bit of parallel. I mean, of course you're not convinced that it's parallel, but if you push the screen to be super far away from it, you can think of it as if you're drawing two lines that are very parallel to each other, extending out from source 1 and source 2 all the way until you reach the screen. Okay, this is the actual situation that you should be imagining. Okay, the diagram is not according to scale. If you really put everything according to scale, these two lines over here, these two paths over here will be approximately parallel to each other. So you can think of it as they are traveling the same amount of distance, except that the first path has an extra bit of distance to travel over here. Okay, if you think of these two lines to be parallel, they will, if they are parallel, technically they cannot meet, right? Okay, this is what you might think, but the fact is it is very far away. So if it looks parallel, but somewhere far away they will converge until a point. Okay, it's very hard to represent in terms of diagram. You might need to imagine the situation. But if you imagine this as two parallel straight lines, so these two parallel straight lines might look like they have the same length, except for this extra bit of distance that path 1 have to travel. So this is the path difference, which is represented by R2 minus R1. Okay, you have to take my words for it, this kind of approximation, because it's really hard to illustrate in terms of diagram. But if I explain to you, you have to use some imagination to make it work. Okay, so this is our R2 minus R1 and it's equals to an integer multiple of wavelength. This is what we have mentioned earlier for constructive interference. Now I'm going to re-represent this R2 minus R1 in terms of this small d, big D and Y that we have over here. I want to change this from R2 minus R1 that is difficult to be measured. We change it to be represented in terms of small d, big D and Y, which can be easily measured. Okay, so first let's focus on this particular angle theta over here. You have this theta over here. Why do I focus on this particular theta? There's not much reason to it. Just follow along. Okay, don't worry too much about it. Just follow along. So if theta is over here, because we know that this theta is formed by two lines intersecting each other, we know that the opposite side of the intersection should have the same angle, which is theta as well. Okay, so theta is over here, causing here to have a theta as well. Now if we focus on this particular triangle, this particular triangle, here, 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 okay, it's a right angle triangle, right? You have a vertical line, a horizontal line, and a line at an angle. So this is a right angle triangle. You know that here it's theta. If you know that here is theta, and here is 90 degree, right? So for sure you know that here will be 90 minus theta. Okay, so this particular angle here will be 90 minus theta. Now I want you to continue and imagine the next right angle triangle that you want to imagine is this particular right angle triangle. Okay, extended by the first path, the perpendicular dotted line, and also this vertical line over here. So this is another right angle triangle. You can see the 90 degrees over here. So this is a right angle triangle. So if this is a right angle triangle and here is 90 minus theta, here it will be 90. So if this is 90, this is 90 minus theta, the small angle that we have here will be theta. So this particular angle here will be theta. Okay, so let me draw it larger. So this one is R2 minus R1 that we discussed earlier. Then after that, we already figured out that the theta should be somewhere around here. Okay, why do I spend so much effort to talk about this theta, how we switch from here to here to here to here? It's because if you look at this diagram here, this is actually a right angle triangle. So this right angle triangle here, we can actually resolve this hypotenuse. The hypotenuse is over here, which is represented by D. You can resolve it into two components. One component will be R2 minus R1. Another component will be this dotted line here. Of course, I believe all of you know that we are interested in R2 minus R1. So we are going to re-express R2 minus R1 in terms of D. Okay, if you think about it, this is actually just R2 minus R1 can be represented by D sine theta. Okay, probably you need me to draw it out, maybe. Okay, if I flip it to be a triangle that looks something like, maybe I put it here. Okay, this is the triangle. So here it will be slit 2. Here it will be slit 1. Then the distance here we call as D. Okay, then this is the right angle over here. Then this will be R2 minus R1. So the theta will be somewhere here. Okay, what I'm doing is just I'm turning this triangle so that it becomes the normal right angle triangle that we usually see. So now if you rotate it to be like this, you can easily see that this D here can be resolved to the vertical component over here and horizontal component over here. The vertical component is R2 minus R1, which is what we are interested in. So R2 minus R1 here is actually can be found or can be determined using D sine theta. Okay, you break it to the y component or the vertical component. So R2 minus R1 is actually equals to D sine theta. So now that you know that R2 minus R1 is equals to M lambda, R2 minus R1 is equals to D sine theta, you can say that D sine theta effectively is equals to M lambda. Okay, so our first objective is cleared. We already changed R2 and R1. We re-represent it with something we can measure, which is D over here. But there's another thing that is difficult to measure, which is theta actually. Theta is actually quite difficult to be measured. So we will try to switch it with other things that we can easily measure. Okay, so theta is found over here. Theta is also found over here. Theta is also found over here. So what I'm going to do right now is I'm going to take another kind of approximation which is very popular in trigonometry. It's called a small angle approximation. Okay, small angle approximation says that when an angle is small, okay, in radian, this whole thing is in radian. If your angle is small, your theta will be approximately equals to sine theta. Okay, and your sine theta will be approximately the same as tangent theta. Okay, this is only valid when the angle is small. Okay, if the small angle means like it's about 5 degree, 5 degree to 8 degrees somewhere, like 1 degree to 8 degrees somewhere around there, nothing exceed 10 degree, I think, nothing too big. Okay, under this requirement that your angle is small, you can actually substitute this sine theta and re-represent it as tangent theta. Okay, it's small angle approximation. If you want to know why, you can discuss with me in class, or you can try to search Google small angle approximation. The explanation is quite simple. Okay, so technically you can substitute sine theta here to be re-represented as tangent theta. Why do you want to re-represent it with tangent theta? Well, if you see here, there's a theta over here. This theta also is inside a right angle triangle, right? This is the right angle triangle that we're talking about. Okay, so this right angle triangle, if you talk about the tangent of it, tangent is opposite side divided by adjacent side, right? The opposite side can be represented by this side over here, which is y. Whereas the adjacent side, it's very, very, very similar to D over here. There's only a small portion that is sacrificed, okay? This line over here, it's very similar to this big D over here. So you can actually re-represent this tangent theta here to be y over D. Again, tangent is opposite divided by adjacent. Opposite is this side over here, which is represented by y. The adjacent is represented by this line over here, starting from this intersect to this screen over here. But if you really go draw the thing according to scale, means by you push the screen to be super far away, you will see that this line over here is actually nearly the same as this big D over here. Means that this small portion here is actually very small, that is actually negligible. We can almost assume that the distance from here to here is the same as this big D over here. So now tangent theta can be represented as y over D. Okay, there's a few approximations that we have already made already. The first one is this R2 minus R1 is over here. That's the first approximation we made, because we say that the screen is extremely far away. These two lines are almost parallel. So that's the first approximation that we made. Then we say small angle approximation, sine can change the tangent. That's the second approximation that we make. The third approximation that we make is that we say that this line over here from this intersect to the screen is actually very similar to the whole line itself. So we can just change it to become big D. Okay, means that this portion is very small. This portion is the significant portion, or it's almost everything. Almost everything is here. A small portion is here already. Okay, so we can almost assume it to be just everything D. Okay, so now that we already changed or substitute the tangent theta to be expressed as y and D, we effectively already changed everything that cannot be measured to everything that can be quite easily measured, I think. Small d is just a physical distance between the two slits. Y is just the distance of the bright fringe from the central bright fringe. D here is just the distance between the slits and the screen. So now effectively you have already derived a new equation to determine y. So if you want to determine the y for the second bright fringe, what you need to do is just put y is equals to 2 lambda d over d, because here is 2 lambda, right? Okay, if you are really caring about the sign, you can put in -2 to get a y that is negative value, but usually we don't really care about the sign. Just calculate, oh, this is the second order fringe or the second fringe, then you just put 2 inside the m, then put in the wavelength of the light that passed through the double slit, the distance between the slit and the screen, and also distance between the two slits. Put everything inside, you can determine y. It can be used for any kind of bright fringe, from the central bright to the first bright, second bright, third bright, so on and so forth. Okay, so this is the equation that we have derived for constructive interference to determine the distance of a particular bright fringe from the central bright. Okay, now if you move on to talk about destructive interference, okay, we move on to talk about the dark fringes. If it's about the dark fringes, we know that destructive interference is still similar. The only thing that's different is the starting point, which is R2 minus R1 has a 0.5 in it. R2 minus R1 has a 0.5 if we talk about destructive interference. If you have no idea why destructive interference there's a 0.5, you might need to review back to the previous videos that we have earlier. So for destructive, R2 minus R1, the path difference from here to here and here to here has a 0.5 wavelength. Okay, it can be 1.5, 2.5, 3.5, any kind of 0.5. Okay, so the rest of the derivation is actually the same. You are going to label that this point here is R2 minus R1, so you are going to change R2 and R2 minus R1. You are going to replace it with d sine theta. Okay, you find your theta the same way, then you represent R2 minus R1 as d sine theta. So once you represent it as d sine theta is now equals to m plus half lambda. Then again, we want to change using small angle approximation, substitute sine theta to be tangent theta. Then tangent theta once again can be re-represented by y over d. So now we can get the equation for y. For dark fringe, the equation is slightly different. For destructive interference, it's different from constructive interference, that it has a plus half inside here. Okay, so if you want to find the distance of let's say this first dark fringe from the central, right, So what you do, you find the first dark fringe, the distance over here, you can just use y is equal to this equation. But because this is 0.5 lambda, you're going to put m is equals to 0 plus half. Then you get 0.5 lambda, right? Okay, 0.5 lambda d over d. Okay, so now I already derived for you two equations. So one equation is for constructive interference. Constructive interference, there's no plus half, there's only m lambda d over d. But for destructive interference, the only difference is you have to add on a plus half lambda inside here. Okay, so these are the equations for constructive interference and destructive interference for a double slit experiment.